I'm going to go back on something I said in the last video. I said in the last video I wasn't going to hold you responsible for convexity. And then I took a close look at how smart all of you all are and your backgrounds and so forth. And I said, man, these folks, they can handle that. So we are going to talk about convexity. And we'll talk about it in this video. And it's not nearly as bad as you might think it is. But before we get into convexity, let's do one more example on calculating the duration and the modified duration of a bond. So let me pull up the class notes here to be able to do that. And so for this second example here, we're going to see a bond. This is page 2 of the class notes on duration, modified duration, and convexity. We're going to see a bond that matures in 6 years, has an 8.4% coupon rate, and its yield to maturity is 9%. So let's now go into Excel, our same spreadsheet we were in before, and use it to calculate the duration and the modified duration of this bond. So we're going to pull that up here. And so here's bond number 2. Has a face value of $100. The coupon rate is 8.4%. It matures in 6 years. The yield on the bond is 9%. And here we're calculating the price from that information. The price is $97.26. If we say that today is February 10th of 2020, the bond matures February 10th of 2026. Using the duration function in Excel, the duration of the bond is 4.814395. Okay. If we then use the modified duration of the bond, and remember, modified duration is going to be the duration divided by 1 plus the semi-annual yield. In this case, the semi-annual yield is 4.5%. So take duration divided by 1.045, and that gives you modified duration that we've got there. So let's suppose, as I've got right on here now, that this bond goes, that interest rates on this bond go up by 2%. So the yield on the bond goes up from 9% to 11%. I tell you what, let's make it something a little bit easier to be able to see. Let's suppose interest rates go up by 1%. Okay, if interest rates go up by 1% from 9% to 10%, modified duration predicts that the price of the bond will go down by 4.607%. There it is right there. Okay, so again, modified duration is predicting how much percentage-wise the price of the bond will change when there is a 1% change in interest rates. Obviously, if there's a 2% change in interest rates, modified duration is predicting twice that amount. If there's a 0.1% change in interest rates, modified duration is predicting there'll be a 0.1% of that amount. So here is the actual change in the price. It goes down from $97.26 to $92.91. It dropped by 4.47%. Modified duration predicted it would drop by 4.6%. So modified duration predicted a bigger drop than was actually there by this amount that is right there. If interest rates, instead of going up by 1%, go down by 1%, then modified duration is predicting the price of the bond would go up by 4.607%. And in fact, it went up by 4.74%. So modified duration is off by that amount. Modified duration, again, is best when we show fairly small changes, like 1 basis point, 0.01%. There. And you can see now modified duration is pretty darn close to predicting what the actual change on the price of the bond was going to be there. So, but it is off. So how can we get closer to this? Okay, well, as I mentioned, what we can do is we can add the convexity measure. So first of all, let's talk about what convexity of a bond is. And let me go back to the whiteboard for this, okay? And we have already mentioned that if this is the price, that's P, price, and yield of a bond, right? The price yield relationship, that it is a that it is in fact convex. So here is a particular bond. We'll call it bond A right there. That is how its price will change as interest rates change, right? Interest rates go up and the price of the bond comes down according to that curve there. Now, let's just say that right here is the current price of bond A, and right here is the current yield on bond A. Now let's take another bond, bond B, which has the exact same price and the exact same yield right now, but it is more convex than bond A is, meaning it's going to look a little bit more like this, okay? So bond A and here's bond B. Bond A and bond B both have the same price right now. They both have the same yield right now, but bond B is more convex than bond A is, meaning that bond B, kind of bends more in that price yield relationship. Now, if you take a look at this and you say, well, which is the better bond to own, bond A or bond B? Well, clearly bond B is a better bond to own because, see, if interest rates go up, both of these bonds go down in price, but A goes down by more than B does. So if interest rates go up, you'd rather own bond B. It's going to go down in price by less. Now, if interest rates go down, both A and B go up in price, but B goes up in price by more. So you would rather have bond B. So if whether interest rates go up or whether interest rates go down, bond B is the better bond to own. So convexity is a good feature in a bond. You like bonds that have more convexity because when interest rates change, whether they go up or whether they change or whether they go down, it's going to be to your benefit to have a more convex bond. If interest rates go up, your bond will go down by less. If interest rates go down, your bond will go up by more. So that's this concept of convexity there, okay? Now let's see how we're going to get this convexity measure added into modified duration here. So we've already seen here, again, this is going to be the price and this is going to be the yield on the bond. And we've got just a single bond here going like this. And we know that if this is currently the price and the yield, then this straight tangent line, as I'm doing as best as I can right there, is going to be, the slope of that line is going to be the bond's modified duration. And we said that if there are just little changes in the yield up and down, it's going to be a pretty good approximation. For bigger changes, it's not going to be such a good approximation. We're going to add to modified duration something called the convexity measure, which is really, it's a second derivative is what it is. We're going to add that to it. And as a result, this dotted line I'm going to draw now will now be our prediction of what the change in the price or of what the new price of the bond is going to be. The dotted line is going to come in here between the curve and the tangent line. And then once we get down here, the dotted line is going to be up above the curve, but it's going to be much closer to it. Okay. Now on this whiteboard, it's not easy to draw a dotted line, but what I've tried to draw for you is that it's obvious to see that if interest rates go down, okay, convexity measure plus modified duration, which is this dotted line, is going to be closer to the true change, to the true price of the bond, which is the curved line, than just modified duration by itself. And if interest rates go up, then the convexity measure added to modified duration, which again is the dotted line, is going to be closer to the true change in the price, the true new price of the bond, which is the curved line, than the approximation given by modified duration by itself. And if the drawing doesn't reflect that very well, trust me, it does that. So let's take an example of how we're going to calculate, or first of all, before we go through an example, let's see how we're going to calculate the convexity measure of a bond. So let's go back to the notes here. And we're going to see that the convexity of a bond is going to be calculated kind of like the duration was. We're going to have the convexity measure is going to be calculated by summing up the present value of the cash flows, okay? But they're going to each be multiplied by the time period in which they occur, multiplied by the next time period. So in other words, if they occur in time period 1, we're going to get time period 1 multiplied by time period 2 times the present value of the cash flows in time 1, and so forth with that. And then instead of dividing by the price, we're dividing by the price times 1 plus R. R is the semi-annual yield squared. So here is that first bond we saw before. The same bond we looked at before that has 2 years until maturity, okay? And so it has cash flows in time period 1, 2, 3, and 4. And if you remember, there was $4 in time 1, 2, 3, $104 in time 4. So to get the convexity measure of it here is this is the present value of the cash flows occurring in time 1. They get multiplied by time period 1 times time period 2. And then these are the present value of the cash flows in time period 2. They get multiplied by 2 times 3. Here's the present value of the cash flows in time 3. So that gets measured, multiplied by 3 times 4. Here's the present value of the cash flows in time 4. They get multiplied by 4 times 5. So that's all in the numerator there. And then what's in the denominator is the price of the bond, 96.454, times 1 plus the semi-annual yield squared there. That gives us our convexity measure, 16.75817, except that, once again, because we are using semi-annual periods instead of years, we need to make a conversion. See, actually, if we were using years, this 1 would have been a 0.5, the 2 would have been a 1, right? The 2 would have been a 1, the 3 would have been a 1.5. So because we have these in here twice, we've got to not just divide by 2, we've got to divide by 2 squared, which is 4. So the 16.75817 gets divided by 4 to give us the convexity measure, which is 4.18954. Now, as I think I mentioned to you earlier, unfortunately, there is not a function built into Excel to be able to calculate convexity measure, but it's not that difficult to be able to do, not for folks getting graduate degrees in business or in finance anyway. So for this very simple bond here, here is how we're calculating its convexity measure. Now, once you get the convexity measure, that has to be added into modified duration to get the dotted line we saw in the whiteboard in a few moments ago. And here is how that works. This formula right here, okay, is going to find the approximate price change of the bond using both modified duration and convexity. So the price change in the bond, and it's and this symbol right there means approximately equal to. It's going to be the modified duration times the change in interest rates, or the change in the yield. So because if interest rates go up, the price of the bond is predicted to go down, we need to put a negative sign in front of the modified duration, because modified duration number is an absolute value number. So if we don't add convexity, this is, with just modified duration, this is what we're looking at right here, okay, right there. It's the price change in the bond is approximately equal to the modified duration times the change in yield, okay? And of course, but we're saying price goes down if interest rates go up, so that's why we have to put the negative sign there in front of modified duration. Now, if we were going to add in the convexity measure, we are adding this over here. So we're adding a number, and the number we are adding is going to be 1/2 times the convexity measure we just calculated, times the change in the yield squared. Now, this is going to have to be a positive, because when whether the yield goes down or goes up, when we square it, it becomes a positive value. 1/2, of course, is a positive number. And the convexity measure, the way we just showed how to calculate it, always has to give us a positive number. So we're always adding something to the modified duration calculation here. And that's why you saw that with modified duration, let's go back for a second to our whiteboard here. when when we saw the dotted line here is always above the tangent line, because adding the convexity measure lifts up our approximation from modified duration to that dotted line, which is modified duration plus the convexity measure. Okay, so let's go back now to the notes. Okay, and we're going to see in the notes what is our approximate price change for this particular bond. It's going to be, okay, the modified duration, which is 1.7955. And let's say there's a 1% change in interest rates. So we put a negative sign in front of the modified duration. The yield change is 0.01. And now we're going to add to it our convexity measure, 1/2 times the convexity measure, of 4.18954, times the change in price, 1% squared. And now our price change is estimated to be 1.7745% compared to modified duration of 1.7955%. The convexity measure added into modified duration will give us a better approximation than modified duration did by itself. To see that, let's go back to the spreadsheet. And here is our spreadsheet, and we're going to go back up to that first bond that we were looking at. This is the bond that only has 2 years until maturity, right? So it had a face value of 100, coupon rate of 8%, maturity of 2 years, yield on it was 10%. Here was the price, okay? And here was the modified duration, 1.795457. Now I'm going to have a very difficult time getting all of this onto the screen at once. So I don't think I'm going to try to do that. We're going to slide over here, and we're going to see that we're calculating the convexity measure on that bond. Here is the time periods, 1, 2, 3, 4. And we got to go to time period 5, because remember, in time period 4, where the cash flows from time 4 are multiplied by time period 4 times time period 5. So here's my cash flows in times 1, 2, 3, and 4. These are my discount factors. That's 1 over R, okay? 1 over R raised to the first, 1 over R raised to the second, 1 over R raised to the third, 1 over R raised to the fourth. So this is going to be the present value of the cash flow. So this $4 gets discounted back to 0. There's the present value. This $4 gets discounted back to 0. There's its present value. This $4 gets discounted back to 0. There's its present value. This $104 divided by 1 plus R, R is 5%, I think in this case, raised to the 4th power is then going to be this number. Now what we're doing here is we're multiplying the cash flow in time period 1 by number 1 and number 2. Here we're multiplying the present value of the cash flow in time 2 by number 2 and the number 3. Here we're taking the present value of the cash flow in time 3 multiplied by the number 3 and the number 4. Here we're taking the present value of the cash flow in time 4, multiplying it by the number 4 and the number 5. Here we are summing them all up, okay? And here we are dividing by the price of the bond times 1 plus R squared, gave us that number of 16.758, which we now need to divide by 4, because our periods were 1, 2, 3, 4, and 5 rather than 0.5, 1, 1.52, etc. So our convexity measure is 4.1895. And then our predicted change in price with convexity is going to be the negative of modified duration multiplied by the price change, the change in yield, plus 1/2 times our convexity measure multiplied by the percentage change in the price squared. And so the predicted change is 1.774. The modified duration predicted 1.795. And look, the price change, the actual price change was 1.7747. That is much closer with convexity added in there. Convexity added in there was 1.7745. So convexity added in does a better job. Now, although when we add convexity in, it does a better job of predicting the price change, most practitioners won't go that far as adding in convexity to it unless they really want to be precise on things. So we're not going to have a lot of examples where we're going to be using convexity, but I want you to understand what it is and how it gets incorporated to give us a more precise approximation of the change in the price of the bond when interest rates change. Uh, when we add the convexity into the modified duration there. So you should be good now to understand duration, modified duration, and convexity.